This video is brought to you by electricalexamcoach.com, offering the #1 electrical exam prep series. We have the pro version with the unlimited testing center and the free version without the unlimited testing center. We have interactive flashcards. We have full online lessons with videos and practice tests at the end. We also have unlimited practice testing on every topic that you can imagine for exam prep. This program comes with 100% full support from us here at electricalexamcoach.com. We just want to see you win. Let's get to it. Hey y'all, what's up? It's the Electrical Code Coach, and I'm super excited to offer this resource to you guys. It's 25 questions with full audio explanations. Before we get started, if you guys could do me a huge personal favor and hit that subscribe button and hit the notification bell button, that way we can spread the word and help more people. With that being said, I want to talk about the best way to use this resource. So each question, I'm going to speak it audibly and it'll list the answers below. But right after I'm done speaking it, go ahead and hit the pause button on the video and try to work through it on your own. And then you can hit the play button and see how I fully explain it and lead to the answer. I am the Electrical Code Coach. And if there's any way that I can help you in life or business, you can just email me at electricalcodecoach@gmail.com. Let's get to it. What size main overcurrent protection would you select with a total calculated load of 42,552 VA on a 120/208 three-phase system? This one's going to take a little bit of thinking. We're going to divide the total VA by the system voltage. But with three-phase, we must do a little bit of pre-work. First, we must take our system voltage and multiply it by the square root of 3 because of the nature of three-phase. So we take 208, multiply it by 1.732. That's going to give us approximately 360. Now we're going to take that, we're going to take our total VAs, divide it by our new number, and that is going to give us 118.116 amps. We would, of course, round down, and we're going to choose the next standard size, and in this case, it's going to be a 125 amp breaker. So, really excited to get into overcurrent with you guys. We're going to be hardcore in overcurrent for the next week or two, leading directly back into ampacity. We're ultimately going to get to the optional method for our load calculations. I just wanted to take a little break. I know we've been doing load calculations for about 5 weeks straight, and I wanted to give you guys a break. Plus, we're building on these processes. I'm so thankful I get to be a part of your guys' journey. Whew, if there's anything you need from me in life or business, just let me know. I am the Electrical Code Coach. I'm here to help you become everything that you can be in life or in business. Let's get to it. How many general square foot VAs would you calculate for a dwelling unit that has 4,300 square foot of main living space with a 400 square foot sunroom and an 1,100 square foot detached garage? First, we're going to determine the total number of square foot that is included in our calculation. We will count the 4,300 square foot of main living space. We're going to count the 400 square foot of the sunroom. We're going to omit the 1,100 square foot garage. Then we're going to do 3 VAs per square foot. We're going to take in total our square foot. It would be 4,300 plus 400. That's going to equal 4,700. Now we take that 4,700 square foot. We're going to multiply it by 3 VAs per square foot, and that's going to give us 14,100 VAs. Great job. And we select A. What is the total general demand for a dwelling unit that has 4,900 square foot with a 4,500 watt dryer and a 10 kW range using the standard method? So first we're going to figure our square foot VAs. We take 4,900 multiplied by 3, and that's going to give us 14,700. Now we're going to add our 2 small appliance and 1 laundry circuit. That is going to give us 4,500 extra VAs, and that's going to give us a total of 19,200. Now we take and apply our 220.42 demand factors. That's going to give us 19,200 minus the 3,000 that we have to calculate at 100%. That's going to give us 16,200. Now we take and multiply that by 0.35. That's going to give us 5,670. Now we have to add back the 3,000 that we set to the side. That's going to give us a total of 8,670. And let's set those to the side up here. Now, when we're doing the standard method, we must use a 5,000 minimum or the nameplate rating. In this case, the nameplate is less than the 5,000 minimum, so we'll use 5,000. Then we're going to do our range. We're going to head to table 220.55. In this case, our range falls in column C, so we're going to use 8,000 as our base. And we're going to add 8,000. Then we total those 3 together. That's going to give us 21,670, and we select D. Great job. What is the total demand for one wall-mounted oven with a nameplate rating of 4,500 watts and one counter-mounted cooking unit with a nameplate rating of 4,500 watts? We're in table 220.55. We're being careful to watch out for words like wall-mounted oven or counter-mounted cooking unit. That's going to send us to a special part of table 220.55, which is in note 4. And in this case, it wants us to total the two ranges and treat them as one range. With that total, we're going to use table 220.55 as if we had one range. So we take 4,500 plus 4,500, and that is going to equal 9,000. Now we head over to table 220.55, and we're going to treat it as if we have one range. When ranges are in between 8 3/4 and 12 kW, we're going to be using column C. Column C for one range is A, 8 kW. Great job. What size main overcurrent protection would you select with a total calculated load of 42,552 VA on a 120 240 volt single phase system? Now this one's going to take a little bit more thinking. We're going to divide the total VA by the system voltage. And with single phase we can just do straight math. So we're going to take our total VAs, we're going to divide it by the system voltage. That's going to give us an amperage of 177.3. Now in this case we can drop the 0.3. We're going to choose the next standard size from our overcurrent protection table, which is 240.6A. And when you go there, you're going to find there is no 180 amp breaker, and the next standard size is 200. Great job. What is the allowable ampacity of a 250 kcmil THWN-2 copper conductor that's installed in a pipe with 9 current carrying conductors in an area with an ambient temperature of 148 degrees Fahrenheit? When we're doing our corrections and bundling adjustments, we're going to start in the 90 degree C column. We're going to find that 250 kcmil in the 90 degree C column is good for 290 amps. Now we're going to head to our respective bundling adjustment table, and we're going to find out that our bundling adjustment for this, for 9 current carrying conductors, is 70% or 0.70. Then we're going to head to our temperature correction table, and we're going to find out that 148 degrees Fahrenheit is 65% or 0.65. Then we take and bear the math out. We take our original ampacity multiplied by 0.70 multiplied by 0.65, and that's going to give us a new allowable ampacity of 131.95 amps, and we're going to select B. What size main overcurrent protection would you select for a total calculated load of 85,250 VA on a 122/40 volt single phase system? So we're going to divide the total VA by the system voltage. And with single phase we can do straight math. So we take our total VA, we divide it by 240. That's going to give us approximately 355 amps. We're going to round down, and we're going to head to table 240.6A and choose the next standard size. And we'll select A. Great job. What size copper THHN conductors would you select for a 50 amp load that's known to run for more than 3 hours, terminating to 60 degree C terminals? It's 3 hours or more, so we must take it at 125%. 50 multiplied by 1.25 equals 62.5. Now we're going to head to our primary ampacity table. We're going to head to the 60 degree C column because it states that we're terminating to 60 degree C terminals. We head there for copper, and we select C. What size parallel copper USC2 conductors and main overcurrent protection would you select for a 920 amp load on a commercial service terminating to 75 degree C terminals? When we're dealing with loads that are 801 amps or more, I want you to head to table 240.6A first and size the main overcurrent device. And the reason that we do that is because, typically I have you size the wire first, right? Enough to cover the load, and then we go select the overcurrent protection. Well, when we're dealing with 801 amps or more, I want you to first select the overcurrent protection because that's going to technically be the load that we size our wire by. So when the overcurrent protection is greater than 800 amps, our wire size must meet or exceed the overcurrent protection. So we're going to select a 1000 amp main overcurrent device from table 240.6A. Then we're going to treat the 1000 amp overcurrent protection as our load. So we're going to head to 75 degree C column for copper. We're going to go through the same process when we're paralleling, starting with the smallest pair. We're going to find out that in this case it's parallel 900 kcmils and a 1000 amp main overcurrent device. Great job. What is the allowable ampacity of a number 10 THWN-2 copper conductor that's installed in an area with an ambient temperature of 142 degrees Fahrenheit? When we're doing temperature corrections and bundling adjustments, we're going to start in the 90 degree C column. We find that a number 10 in the copper 90 degree C column is good for 40 amps. Now we're going to head to tables 310.15B2A in the 2017 and table 310.15B1 in the 2020. Same table, new name. We're going to find the temperature correction factor. This is our temperature correction factor table. We're going to slide down to our new ambient temperature, being sure to start on the Fahrenheit side, which is on the right-hand side of the table, because our degrees are listed in Fahrenheit for our ambient temperature. Then we're going to slide over and tee off with the 90 degree C column that has the correction factors in it. So we're going to find 0.65 is our correction factor. Now we're going to take our original ampacity, we're going to multiply it by 0.65, and that's going to give us a new allowable ampacity of 26 amps. And we select B. What is the total VA before demand factors of the following appliances using the optional method? The nameplate ratings of a 1400 watt dishwasher, 11 kW range, a 4800 watt dryer, and a 4500 watt water heater. So we're not going to use the 4 or more 75% rule because it doesn't apply in the optional method. When using the optional method, we're going to use the nameplate ratings of the appliances. So we take them, we just total them up. Again, this question asks for the VA before demand factors, and we're going to select C. Okay, so let's look at variation 1. This is going to be 100% of the AC or 100% of the heat pump if there is no supplemental heat. What is the total HVAC demand you would calculate for a dwelling unit with an AC compressor rated at 22 amps and a heat pump compressor rated at 25 amps, both using a 2.2 amp blower motor on a 122/40 volt system using the optional method? So first we're going to calculate the AC. So we take our 22 amps multiplied by 240 volts, and that's going to give us 5,250 VAs. Now we're going to take and multiply out the blower motor. And so it's 2.2 multiplied by 240. That's going to give us 528. Now we just take and add those two together, and that is going to give us our total AC load. Now let's go ahead and calculate the heat. So we're going to take 25 and multiply it by 240, and that's going to give us 6,000 VAs. Then we're going to take and this is going to be our largest motor, we're assuming, in this calculation. I have you guys do that just for good practice, and that's going to give us 6,000 multiplied by 1.25. That's going to take that up to 7,500. Then we're going to add in the blower motor, and that is going to give us another 520 VAs. And then we take and add that all together, and that's going to give us 8,028 total heat. Remember, in this case, we select one or the other, the larger of the two, and we are going to select A. Great job. What size copper conductors would you select for a 3 horsepower, 208 volt, 3-phase motor that has an FLA nameplate of 9 amps terminating to 75 degree C terminals? Remember, when we're sizing normal motor conductors, we're going to use the FLC. For conductors that have motors that are 1200 RPM or less, intermittent duty, multi-speed, or for high torque, you will use the nameplate current rating. I just want you to have that in the back of your mind. This week, and when you're dealing with normal motor conductors, we're going to use the FLC and not the FLA nameplate. When we're dealing with a certain special sect of motors, we will actually use the FL nameplate. I wish the code book wasn't like this. I wish they would just pick one or the other and just stick with it, because it makes it very hard when you're testing. But I'm going to teach you this week and reteach you, because remember, we've learned this in the past. This is the Master Series. This is all about you already knowing this much, but I do want to recap so it's fresh on your mind, right? All right, so let's go ahead and jump in. All right. Also, when we're doing normal single motors, we're going to multiply that FLC by 1.25. We're going to be doing some multiple motor questions next week, but this week we're going to be doing all single motors, meaning one motor, and we're going to be doing normal conductor sizing. So let's go ahead and jump in. All right, so back to our question here. First, we're going to find our FLC listed in 430.248 for single phase and 430.250 for 3-phase. Well, in this question, our question is 3-phase, so we're going to head over to 430.250. We're going to slide down on the left, and we're going to select our respective horsepower. Then we're going to tee off in the right for our respective voltage. Make sure you use a piece of paper so you don't get off, and you tee off at 208 volts. And we're going to find that our motor FLC for this motor is 10.6 amps. All right, now we have to multiply it by 1.25. So we're going to take 10.6, multiply that by 1.25, and that's going to give us a new amp draw of 13.25. That's going to be the amperage that we size our wire by. Okay, so we take that 13.25. Now we've got to head to our primary ampacity table. You're going to be in 310.15B16 in the 2017, and you're going to be in table 310.16 in the 2020. What we're going to do is we are going to head to the 75° C column. When you are dealing with motors, you are going to select the conductors based on whatever the terminal rating is. So if it says 60, 75, or 90, whatever it states, that's what you're going to be selecting from for your question. All right, let's go ahead and jump right into it. In this case, we come down, we find that a 14-gauge wire in the 75° C column is good to cover our 13.25 amps, and we select A. Great job. What size short-circuit ground fault protection would you select for a 5-horsepower, 208-volt AC 3-phase motor terminating to 60° C terminals with a nameplate FLA rating of 26 amps using an inverse time breaker? We never size normal short-circuit ground fault protection from the nameplate or FLA rating. It's just like normal circuit conductors. You're going to size it from the motor FLC. If the FLC is printed on the nameplate, we can use that. First thing we're going to do is go figure out what our FLC is. We know how to do this. Pause the video now. See if you can find out the motor FLC. So we use our FLC motor tab. That takes us to table 430.248. We're doing 3-phase, so we need to flip over to 430.250. We're going to look down and find a 5-horsepower motor. Then we're going to slide over to our respective voltage. And in this case, it's going to be a 16.7 amp motor. What size short-circuit ground fault protection would you select for a 7.5 horsepower, 460-volt AC 3-phase motor terminating to 60° C terminals with a nameplate FLA rating of 9.9 amps using an inverse time breaker? Remember, we're always going to use our FLC and not the nameplate FLA rating when sizing normal, short-circuit, and ground fault protection. We're going to head to table 430.248 for single-phase and 430.250 for 3-phase. We're going to find that our FLC in this case is 11 amps. Now we're going to head to table 430.52. We're going to tee off with our motor and our type of device, and we're going to find that our multiplier is 250%. So we take our FLC, multiply it by 2.50. That's going to give us 27.5 amps. Now we're going to head to table 240.6a, and we're going to choose the next standard size. And in this case, we're going to select C. Great job. What size overload protection would you select for a 5-horsepower, 120-volt AC single-phase motor terminating to 75° C terminals with a nameplate current rating of 54 amps? That's the section in the code that we're going to be working from throughout this entire video today. So if there are service factors or temperature rises listed, you're going to apply the respective demand factor. If there are none listed, it's going to fall under the category of all other motors. Now we're in 430.32A1, and we're dealing with that section right there. All right, so for this motor, it falls under all other motors. We're going to use 115% demand factor. So now we're going to multiply. We're going to take our nameplate FLA rating. We're going to take it and multiply it by 1.15, and that's going to give us 62.1 amps. Now, do they make a 62.1 amp breaker or fuse? No, they don't. So, can we use the next size up? And the answer is no. With motor overload, we must use the next size down. So we're going to head over to 240.6a, and we're going to select a 60 amp overcurrent device. Great job. What size round octagonal box would you select for 9 number 12 conductors? All right, so we've got some options here, and D is never an option, okay? This is the whole point of the Master Series, is we are going to master this stuff. All right, so let's all head to table 314.16a. We're going to be starting there, okay? Head to table 314.16a. We're going to be on page 176 of the 2017 and 184 of the 2020. So go ahead and flip there now, and we're going to look at this table together, kind of recap the table, okay? So if we're staring at this table, it's the larger table on top, and it's 314.16a, and it says metal boxes. But, I mean, these rules apply, you know, across the board. Let's go ahead and look at it. On the left-hand side of this table, there's a large column. It says box trade size, okay? So this is going to be the trade size of that box. If you look there on the left, you see millimeters in the black bold heading. Just to the right of that, you see inches. And that's what we're always going to be dealing with here in the United States. I've never seen a question in millimeters. Okay, so if you look down that inches column, it gives you a bunch of common box sizes. 4-inch by 1 1/4 round octagonal. Go down to the next section. Those are talking about 4 square boxes. You go down to the next section. It shows the 4 11/16 boxes. You go down and it starts showing device boxes. Now, right under that inches part is going to show you the dimensions. But if you look just to the right of that, it's going to tell you the type box. You got round octagonal, you got square, you got device, masonry, gang box, and so on and so forth. Now let's move over to the next complete column where it says minimum volume. Okay, so this is the minimum volume. And we're going to do inches cubed. If you notice there's centimeters cubed and inches cubed. We're always going to be dealing with the inches cubed column. And I show you how to highlight this in my how to highlight video. You can actually check it out in the link in the description below. All right, so when we look down through this, we're going to see all of the inches cubed. And each one of those slides over and tells you the total volume of that specific box. So let's go to the first one. It says 12.5. When we slide over, that's letting us know that there is a total of 12.5 cubic inches for that round octagonal box. And if you slide over, it'll tell you what dimensions they are. It's the 4 by 1 1/4. So 4-inch round, 1 1/4 deep, done. Okay, it has 12.5 cubic inches in it. Now let's go over to the next large section of that table there. Across the black bold heading, it says maximum number of conductors. Okay, and they're arranged by wire size. So if you go down, just down to the next cross column, you see 18, 16, 14, 12, 10, 8, 6. Those are the AWG. That's the size wire. And then if you look down underneath that, that is the conductor count. So let's start. Go to 12. All right, you see the 12 gauge right there on the right-hand side. And if you go down one row, it says 5. Okay? That is the number of conductors, and if you slide over and tee off, that's the number of 12-gauge conductors that can go in the round octagonal box. And if you slide over again to the left, it shows you that it is the 4 and 1 1/4. So in the 4 and 1 1/4 round octagonal box, we're allowed to fit 5 number 12s. Well, if you slide over to the left, you're allowed to fit 6 number 14s. If you slide over to the left, you're allowed to fit 7 number 16s. Do you see how that works? So starting from left to right, it shows you the dimension of the box, the type box, it shows you the total cubic inches, and then for each respective conductor, it tells you how many you're allowed to put in that box. Okay, so that's the breakdown of this table. We're going to work through some questions this week, looking at all the different, angles that you can be asked questions just about this table right here. And next week, we'll start adding in devices and yokes and all these different things to add some of the count. But this week, I just want to work through this table together. We're going to work through it slowly, and we are going to figure this thing out. Let's get to it. Let's do one more before we move on. What is the cubic inch volume for a number 12 conductor? Same process. We're going to go to table 314.16b. We look at the black bold heading and make sure that we're in the correct table. We start on the left-hand side, and we're going to find our respective gauge wire. Now, this is when it's really important that you use a ruler or a piece of paper as a straight edge to make sure that you don't get crossed. So we find a 12-gauge conductor. We use our sheet of paper as a straight edge, and we're going to find that a 12-gauge conductor counts as 2.25 cubic inches as far as box fill volume. Great job. What is the total cubic inch volume you would calculate for a light box that contains 3 12-gauge conductors with 1 stud and 1 hickey present in the box? So the first thing that we're going to do is we're going to figure out what the cubic inch volume is for a 12 gauge conductor. As we learned last week, we're going to head to table 314.16b. We're going to come down, we're going to tee off with 12 gauge, and we're going to find that each one is rated at 2.25 cubic inches per conductor. Now we have to get a total count. Well, if we look at our question, we see right off the bat that we have 3 12 gauge conductors. Okay, so we go ahead and write that down. Now we need to figure out how many more to add for any associated equipment or fittings. So in this case, we have 1 stud and 1 hickey, and we just learned that each one of them counts as 1 based off the largest conductor in the box. Well, we have all the same size conductors, so it makes it a little bit easier. So we count each one of those as 1. So we're going to count our 3 base conductors. We're going to add our 2 fittings, which equals 2, and that's going to total together to equal 5. Now we take that and multiply it by the 12 gauge volume. 5 multiplied by 2.25 is going to give us 11.25 cubic inches. Then we're going to select C. Great job. What is the total cubic inch volume you would have for a box that contained 2 hot conductors, 2 neutral conductors, and 2 equipment grounding conductors, all 12 gauge wire in the 2017 code? So we're going to be referencing table 314.16b. We're going to first count our conductors and see how many there are. So we have 2 hots, we know that they're going to count. We have 2 neutrals, we know that they're going to count. And we have 2 equipment grounding conductors. Well, the code states that we only have to count it as 1. It doesn't matter how many's in the box. It only counts as 1 of the largest conductor that's in that box. So in this case, it's going to count as 1 number 12. So first, let's total our conductors. We have 5. Now, we're going to head back to table 314.16b, and each conductor is 2.25 each 12 gauge conductor. So we take our total conductors, we multiply it by 2.25, and that's going to give us a total of 11.25 total cubic inches for our cubic inch count. And we're going to select C. Okay, let's start all over. How many, number 4, RHH conductors can you fit inside of a piece of 1.5 inch RMC? So the first thing that we're going to do is we are going to head to our NEC tab. And if you do not have that, if your state allows you to make your own tabs, just make your own NEC tab. So we head to NEC. We're going to find our type of pipe. We're going to make sure that the at-risk is not listed next to the RMC. Then we're going to find our page number, and we're going to flip there. When we get there, we're going to find our type of pipe, make sure that we're in the right column, and then we're going to make sure that we're in the right table, make sure we're not seeing an at-risk up there next to the table number. Now we're going to find our insulation type and pipe size. So we come down, find our conductor size, our insulation type, and our pipe size, and we are going to tee off, and we're going to find out that you can fit 6 number 4s in a piece of 1.5 inch RMC. Great job. What is the approximate area in inches square of a number 12 THHN conductor? All right, so here we've got some options. Now, the first thing that we're going to do when we're dealing with different sizes or insulation types, we're going to use Chapter 9, Tables 4 and 5. In this case, it's wanting to know what the approximate area in inches squared of a number 12 THHN conductor. So in this case, we're going to head to Table 5. So when we get to Table 5, let's go ahead and talk about it. You should have a tab that is for Chapter 9, Table 5 if you use the tabs that we recommend. So when you get there, you're going to find basically, kind of the same setup that we've seen before. We have the conductor insulation on the left-hand side, then we have the size wire. But when we look across the top of the table, we have to be careful here that we're choosing from the approximate area section. So if you notice the top black bold heading, it says approximate area. And if you've used our video on how to highlight your code book, we taught you how to highlight this table so it pops and it's easy to use. All right, and we have to make sure also that we're using, underneath the approximate area, that we're using the inches squared, not the millimeters squared, okay? So we want to be using, the only 3 parts of this table we're going to be using is the left-hand side where you select the insulation rating, the next column over where you select the gauge wire, and then you skip a column and you're going to use the inches squared for the approximate area. Okay, pretty simple. So in this one, we need to find our insulation rating. In this case, it is a THHN. So we're going to slide down here on the left-hand side until we find THHN. We're going to use a piece of paper as a straight edge. until we find the 12 gauge conductor, and then we're going to come over and we're going to tee off with the approximate area in inches squared. And in this case, we find out that the approximate area of a number 12 THHN conductor is 0.0133. That's how much space it takes up in inches squared. Let's get to it. What is the available fill area in inches squared of a piece of 3/4 inch Schedule 80 PVC with only 2 wires installed? So we're going to use our Chapter 9 Table 4 again. We're going to head to Chapter 9 Table 4 and we're going to find our type of pipe. We're using the black bold headings until we find the name of our pipe. In this case, we're dealing with Schedule 80 PVC. So when we find it, we look across the top of the table. The first one is over 2 wires. The second one is 60%. The first 1 wire is 53%. And then when you get to 2 wires, you're only allowed to fill up to 31% of that pipe. Then we use a straight edge and we're going to tee off with our size pipe. The trade size is on the far left-hand side. We're going to find 3/4. We're going to come over and we're going to tee off with 2 wires. And we find that it is 0.127. Great job. What size copper grounding electrode conductor would you select for a 100 amp service with a number 4 main copper service conductor? So the first thing we're going to establish is, does it mention the type of electrode in our question? And in this case, it doesn't. So we're going to use table 250.66 at face value. If you've tabbed your code book, you're likely going to have a GEC tab. If you haven't tabbed your code book, then you're going to be on page 116 of the 2017 and page 123 of the 2020. If you're on previous or later versions in the code, don't worry. These tables haven't changed in forever and they're not going to change anytime soon, so you can follow along just the same. All right, so now when we get to the table is when we have to really be careful. The first thing we're going to do is we're going to read the first black bold heading to make sure that we're in the right table. It says Grounding Electrode Conductors. Boom, I feel like we're in the right spot. Now, how we read every table is from top to bottom and left to right, using our black bold headings to navigate the table. Okay, so now we have to go back to our question and select very carefully. So we have a copper grounding electrode conductor and we have copper service conductors. So we're going to use the copper columns. First thing that we have to do on the far left-hand side is we have to establish what section right there our service conductors fall in. Okay, so we have a number 4 service conductor. So ours falls in to number 2 or smaller. Okay, now we need to make sure that we're careful to go over to the copper GEC side of the table to make our selection. So we come over, we slide over with our finger, we tee off at copper, and we're going to find that we're not required to have larger than a number 8 for this size service with these main service conductors is the most important point when we're sizing grounding electrode conductors. Great job.